you ever wondered what's really going on inside those huge data centers for large distributed training? As a data storage specialist, I wanted to look at AI infrastructure through the lens of IO operations. That's why I came up with a 4-tier data flow architecture to explain how it typically works within a complex and modern AI setup today. We will follow the data's journey from the slowest, cheapest archive storage all the way to the super fast memory right on the accelerator. So let's start at the top, tier 0. This is the main place where the actual computing happens. There are two main parts here. The CPU with its system memory, we usually call it DRAM, and the accelerator like a GPU or TPU with its own special high-speed memory, often called HBM or high bandwidth memory. The CPU handles many general tasks and gets data ready, while the accelerator with its dedicated fast memory handles the huge calculations that can be done at the same time. For example, Google Cloud's A4 instances have advanced GPU with HBM, providing the high-speed memory access needed for AI. HBM3E can give you up to terabytes of data per second for each GPU. These accelerators, whether in the cloud or on-prem, are often linked together with special fast network for large-scale distributed training. Also, different parts of a big model might live in the memory of different accelerators, spread across many within a server and across many servers, usually in a cluster. The key thing about accelerator memory is its closeness to the compute cores and its speed, which lets it feed those cores really fast. So if the accelerator's high-speed memory is where data is being processed and crunched, tier 1 is like the waiting area. It's usually made of local NVMe SSDs connected over PCIe, and it helps both the CPU and the accelerators. Its job is to get the next set of data ready so it can be loaded into the system memory or the accelerator's memory quickly. So in cloud environments like Google Cloud, GPU-based VM like the A4 instance, A4 high GPU 8G machine can have up to 12 terabyte of local SSDs. This acts as a very fast caching area. This idea of high-speed directly attached storage is also seen in on-premises AI servers, which often have many PCIe Gen 5 NVMe SSDs. Looking ahead, a really interesting new development that I think will become more and more important in this tier is CXL or Compute Express Link. While it's not widely used yet, it's starting to pick up steam. So, what could make CXL a big deal? It lets the system and memory expanders and even some accelerators using the PCIe bus. This means both the CPU and down the road maybe even the GPU can get to a much larger shared pool of memory with a very quick response times. Basically, it lets devices use this extra memory like it's right there on the chip, which can be very useful for the bigger AI models and data we are seeing these days. This improvement is closely linked to how PCIe keeps getting better. Current systems are using Gen 5 and Gen 6 is coming soon. Each new generation pretty much doubles the speed of the one before it. Okay, so where do all the local tier 1 SSDs get their data? They get it from tier 2, the main storage for the entire AI cluster. This is your high performance shared storage, the whole training data set, which can range from tens of terabytes to hundreds of terabytes or even several petabytes lives here. The main challenge is delivering a high total data speed over a special network to hundreds or thousands of accelerators all at once. A flexible way to do this, especially in cloud environments, is using object storage like Google Cloud Storage as the primary place for these large data sets. This object storage can then be accessed using a standard file system interface, for example, with Google Cloud's Cloud Storage Fuse. For the most demanding jobs that need specific file standards and top speeds, cloud providers, including Google Cloud, comes with services like Managed Lustre, which is a dedicated high-performance file system. This setup is similar to on-premises system that might use distributed file systems like Lustre, Weka, Vast Data, or IBM Spectrum Scale, often built on large arrays of flash storage. Things are changing quickly here, mainly two ways. First, networking speeds keep increasing. Second, the file systems themselves are getting smarter about data placement and how they integrate with object storage. In some cases, we also see distributed file systems acting as a cache layer right alongside GPU instances. So there's plenty of innovation happening. Finally, we get to tier 3. Capacity and archive. This is where data goes for long-term storage when it's not being actively used in training. You might wonder if you even need this tier, especially if your primary training data set is not super large. But in AI, the model's training data is often just the tip of the iceberg. It's everything else, the numerous checkpoints, experimental runs, detailed logs, and potentially vast amount of raw source data that can really pile up. This is where tier 3 shines. Characteristics here are a huge amount of space and the lowest possible cost per gigabyte. This tier is often implemented with object storage in its most cost-effective forms. Moving data from tier 2 to tier 3 is called archiving or tiering, and it's often automated based on data access patterns. All right, so there you have it. From the very cheap, large archive storage in tier 3 through the high-performance shared file system in tier 2, cached locally in tier 1 for both CPU and accelerator access, and finally used by the accelerator from its own super fast memory in tier 0. The main point is balance. Balance between the cost and performance. As you might have guessed by now, tier 0 operating at nanosecond level and tier 3 at seconds to many minutes level. A slowdown in any one of these tiers can waste millions of dollars in accelerators doing nothing. I hope this gave you a good way to picture how data moves in an AI system, but we have really only just started. So I want to hear from you. What part of this stack do you want me to dive deep into next? Distributed file system, how to build and test them, or maybe how the costs work for object storage classes? Let me know in the comment below. If you found this video helpful, please hit that like button and subscribe for more deep dives into data storage technology. Thanks for watching.